When we talk about molecules, we can use Lewis electron dot structures to describe the molecules. And those dot structures are actually pretty predictive. From the Lewis dot structure, you can get a lot of information about the geometry. You can get steric numbers, what kind of things a central atom has to accommodate, and how those things will be arranged in space. But there are limitations, obviously, to our Lewis dot structure picture. Electrons aren't dots and bonds aren't little sticks. So we have to go beyond that to a real quantum mechanical explanation of bonding. Our quantum mechanical explanation of bonding will have the electrons behaving like quantum mechanical particles, particles that have wave-like properties. And when those wave-like properties overlap, they can have constructive interference. They can add together. The amplitude of a wave function can increase when electrons get close to each other. The amplitude increasing leads to a higher probability of finding electrons. So we can take our atomic description of electrons, our atomic orbitals, and apply that to molecules by using atomic orbitals to describe bonding. So let's see how that would work. In the simplest case, hydrogen, H2, that's a molecule, we understand the hydrogen atom. It has a 1s orbital. So let's bring in another hydrogen. Let's make a hydrogen molecule by bringing together two 1s orbitals. When we bring in those two 1s orbitals, now here I've represented them both as green. And remember, orbitals have, the wave function will have a sign, either positive or negative. For the 1s orbital, there are no nodes, so the wave function is the same sign everywhere. And I've drawn that as green everywhere. So green is plus, green is plus. These are two wave functions coming together that have positive sign everywhere. As you bring them together, those wave functions can add. The waves, the electrons, can add constructively. The amplitude between the two nuclear centers can increase. A higher probability of finding the electron between the atoms. When that occurs, that'll look something like this, where I've added the positive amplitudes to get a larger amplitude in the center. Now, that's what we call a sigma bonding orbital. Sigma, like the Greek S, coming from the s orbitals. Another way to think about this is to add them with a negative sign. Here I'm going to add the opposite, bring a 1s and plus a minus 1s. So this red represents that this wave function is negative everywhere. So when these two amplitudes overlap, there could be destructive interference. A positive overlapping with a negative, adding to 0. So there'll be a node in the center, a place where the electron density goes to 0 in the center of this orbital. And we'll call that an antibonding orbital. Sigma star for antibonding. Now when you do the mathematical calculation, you actually find that the sigma combination, where you brought a 1s and a 1s together, added them, and got this increased amplitude, that's lower in energy than the atomic 1s orbitals. And the sigma star, the antibonding orbital, is higher in energy than the two 1s orbitals. And you would guess that because there's a node in this orbital. And remember, the more nodes in an orbital, the higher the energy in general. So a sigma bonding and antibonding orbital can be formed by adding and subtracting the 1s orbitals. Now we add and subtract because we're taking linear combinations, but we can't lose any orbitals in the process. If we start out with two orbitals on the atoms, we have to form two molecular orbitals. The number of orbitals is going to be conserved. So we need the plus and minus combination to conserve our number of orbitals, forming our bonding and antibonding molecular orbital. We can take the electrons then from the atoms and add them to our molecular orbitals. These combinations, when they're overlapped appropriately, give me my sigma bonding and sigma star antibonding orbital. How will the electrons from the atoms fill the molecular orbitals? They'll use the same rules we had for the atoms. They'll go into the lowest energy first. They'll enter orbitals spin paired before they pair up. The same kind of rules, Hund's rule and the Pauli exclusion principle that we used previously. So I'll have hydrogen as a molecule, 2 electrons in a sigma bonding orbital. So where the hydrogen had unpaired electrons, hydrogen atoms had an unpaired electron and was paramagnetic. Paramagnetism indicates an unpaired electron with its slight magnetic field. Hydrogen molecules will be diamagnetic. The electron spins will be paired and cancel each other out. So already we have a prediction from our quantum mechanical understanding of bonding that hydrogen atoms are paramagnetic, hydrogen molecules are diamagnetic. We can continue and look at hydrogen, helium, lithium throughout the periodic table and use our understanding of bonding and adding and subtracting, taking linear combinations of atomic orbitals to form molecular orbitals. And that's what we'll do in this lesson.